So we shall start now. Thanks all for coming for more networking fun in this room. I'd like to welcome Thadeu Cascardo, who's going to tell us more about Open vSwitch and Userspace. Thanks, and go ahead.
Okay. Thanks a lot. So I'm going to talk about Open vSwitch, the architecture, design of how it works, how the daemons work. And I had a hard time figuring out at which level I would show you that. I wouldn't like to show you lines of code, that's too boring. Lucky you, I won't show you. But if you want to, you can start digging because it's like a 400,000 of lines of C code, about 800 files. Including C headers, plus another 600 files of test hits and building and stuff like that, documentation. I only know a very tiny piece of that, so I am wrong on the internet right now, right? So please correct me if you get a chance. Later. And sorry, that's not a talk about DPDK. I'm going to mention about that. So for those who don't know, and just so we get an introduction what we're going to talk about that. So Open vSwitch can be programmed with OpenFlow. It's a network switch for virtual networks mostly. It can be used for real hardware switches, so I'm going to show you how that could be done. So if you have plans in your future to work on a hardware switch with OpenFlow, good luck. It supports data path acceleration for Linux. Jerry has talked about some about that. I'm going to talk more about Userspace here, but I'll show you how the design allows that data path acceleration to work. And since it's a virtual switch, you don't have the ports hard-coded as in a hardware. So you need a way to configure those ports, and OpenFlow does not allow you to do that. So they built another protocol. It's an RFC. It uses JSON RPC. So there you go. JSON is embedded in your switches right now. Okay. So it uses something called ovsdb, which I'll show you a little. So here's a well, it's not a 10,000 mile. Okay, it's 3 kilometers. 3 kilometers view of Open vSwitch. So you see there, OVS vSwitch D is the main component here. When you're using Linux, you set up the flows. So there's that communication right there. It has the ovsdb server, which serves all of the configuration of the switch. And the yellow boxes are the utilities that you can use. So OVS OFCTL is basically a very small OpenFlow controller that you can use to program vSwitch D. OVS vSCTL, it's a very small OVSDB client. It's used to program the OVSDB server, which talks to vSwitch D, so it notifies vSwitch D that the configuration has been changed, and then vSwitch reacts to that. And the DPCTL allows you to carry the state or change the state of the data path acceleration in the kernel itself. So here's your 3 kilometers view. And I forgot to mention OpenFlow controllers. That's how you're supposed to program vSwitch D. So here's a one meta view. I considered putting the complete call graph of the code here, but I guess it would take many hours to generate. Okay, so so here's the little sketch of some of the things. So I won't bother you with this because it's hard to read. Okay, there are better ways to read into this. I'm gonna show you. That's some ASCII art. Okay. So I'm going to show you a better view of these, exactly these, and going to explain what every piece here does. But there are many things here that are missing, because from 1 meter you can see them. Okay, it's all zoomed. So you'll see all of these, and then I realize that's a lot of stuff. I've got to take a step back and start looking at how everything works. I'm going to mention some of the features that you may be interested in, and that you may, I may give some pointers on where to find the files to work with that. So here we go, ovsdb. So what is it? It's the protocol. As I mentioned, it's documented on RFC 7047. It allows you to create new data paths, new bridges, configure the controllers that are going to be used to communicate with those bridges. Then you create and add ports to bridges, create queries, quality of service, and collect stats. So I'm going to give a quick demo on that, on how I use ovsdb. So let's take a quick look here. Okay, so ovsdb-STL is the ovsdb client that talks to the database. So here we are not exactly talking to the switch daemon. We are talking to the database server. So it shows here just a summary of the data paths and bridges that we have. We have a bridge BR0, which has port foo1 and VXLAN0, which has some options there. Bridge outBR, which has 2 ports, an internal one and Ethernet interface. So here's how you get, for example, the stats for ENS3. So you have 0 collisions, number of bytes received, bytes transmitted, and all this stuff. So the ovsdb allows you to carry stats as well. It's a database, it has a schema and stuff like that. So get allows me to read a table, which is called interface. I want the column of the table, which has the ENS3 name. And I want the line ENS3, and I want the column statistics. Okay? So, and then you can set, for example, OF port request. Allows you to tell that for that given port, you want OpenFlow to recognize that port as the number 3. So you may have seen a lot of OpenFlow rules that specify that a given flow is going out for port 3. So what is port 3? So what's that port? So that's how you specify that ENS3 is going to be given that port number. So OpenFlow on vSwitch, it's not persistent. So you're supposed to use an OpenFlow controller for that. Okay. Packets can flow to and from the controller itself. So switch daemon may receive a packet and have a flow there that tells it, well, I don't know what to do with that, or the controller has more logic to decide what to do with that. It's given to the controller in band or out of band, and then you get it back. OVS has a lot of extensions. Most of them really, really needed because OpenFlow is not enough for a lot of things that OVS does. So one of the examples, I guess that they have a hard problem that sometimes the packet flows to the controller and the controller gives it back to the switch daemon, which should not follow all the tables all over again, should continue from where it stopped. So there's an extension that's planned, and it's probably going in 2.6. Basically, OpenFlow allows you to configure a set of matches and actions. So for a given package that matches that given flow, you're going to execute some actions. And one of the funniest actions there is the normal action, because the OpenFlow specification does not tell much about what you're supposed to do with the normal action. It's basically, it's like what a normal switch would do, okay? So what a normal switch does. And in OVS case, we do IGMP snooping, for example. So that's one of the things that normal action is going to do, and if you do not use it, you're going to lose it, okay? So here are some examples. If you've been to, I've been to like three talks already that showed some OpenFlow rules, so gonna save you from that. So porting. So here we go into more detail into how the vSwitch daemon works. So there's this file, porting. It's a markdown file where you can read most of the things that I'm going to talk here. I'm going to try to go into some detail and try to show you how exactly it works. So the switch daemon basically reads from the database and talks to OF-proto. So OF-proto is something that's below the daemon itself. So, okay, ASCII art. Much better than the other one, right? It's the same thing as this one, okay? It's the same thing. This one is much, much better. So, so basically, this switch is talking to ovsdb server, getting all the configuration, and then it uses OF-proto to tell the underlying layer to set up the bridges as they're supposed to. Okay, that's easy, right? But what does OF-proto provide? So basically, it talks to OpenFlow controllers and talks to an OF-proto provider. So the OF-proto provider can be almost anything. So for example, it could be a hardware switch. It could even be another switch to which you talk using OpenFlow itself. Okay? We've been a very nice driver for OF-proto. So you receive OpenFlow and talk to another OpenFlow switch. Okay? It would be very fun to do that. Well, and the other thing that OF-proto does is talk to NetDev, which is a very simple library which wraps communication with a NetDev provider. And there's a lot of them. So if you want to add a port to a switch, you set it up in the database. Now the switch daemon knows that you need to add a port, tells that to OF-proto. OF-proto creates a NetDev device, gets its MAC address, saves it up in the database. Okay, so there's all these things going on here, but when you have this look, it looks very, very simple. But then you have this one, right? Shows almost the same thing, but then you realize that below the OF Proto, we have a real provider. Below the NetDev, we have real providers. This art comes from porting as well. Very great piece. So how to implement an OF Proto provider? There's a lot of layers inside of that. Okay, that's why you need 400,000 lines for OVS. More about DPIF. So the data path interface is the only OF Proto provider that we have upstream. Of course, we have a lot of OVS users around. Many people probably have ported OVS to hardware switches, but they didn't provide anything upstream. So that's the only provider that we have the code there to look at and see what is the F Proto provider supposed to do. And DPIF is very, very complicated. As you notice here, you have OF Proto DPIF, then you have a DPIF, and then you have DPIF provider. So 3 drivers that you can use for OVS. The good thing is that DPIF provider is very, very nice. It should work with the NetDev as well. So NetDev, besides allowing you to create ports, allows you to receive and send packets to those ports, those network devices. If you have such a NetDev provider, then you're all set up. You can use OVS. I'll show you some of the drawbacks about using that, but it's really, really possible to use only that and get everything set and working really, really nice. DPDK uses that. So how do you introduce DPDK support to OVS? You just write a NetDev provider, that's done. Okay? You don't need to worry about writing a new DPIF provider or a new OF Proto provider. Everything is being done for you. So basically, one of the DPIF providers is DPIF NetDev, and how it works is that it reads packets directly from the interface, from the NetDev provider, and then deals with that. Okay, so I'll go more into more detail for that. And one of the advantages of using that is the number of features that you have. For example, bonding, LACP, multicast snooping, contract, all of that is available if you're using DPIF. If you are going to write a new OF Proto, you're going to do that all by yourself. Okay? So these set of features here, and a lot more features are only available if you're using DPIF. If you're not using, if you're going to write your new OF Proto, then you need to rewrite all those features or count on your data path switch to provide that. So here we can see a clear separation from the control plane and the data plane, which is OF Proto. Because OF Proto talks to the control plane using OpenFlow, and it talks to the data plane below that. So your data plane needs to support all of those features, and that's what DPIF does. One of the DPIF providers is DPIF Netlink. Talks to the Linux OVS module, sets ports and flows. Basically, that's what it does. It receives packets that miss those flows, and then set up new flows. I'm not sure if I have, I don't have anything showing an image of that. So basically, well, if fact, I do. That it's here. So, so the data path is here in the kernel itself. Whenever you receive a packet on a Ethernet port, on a physical NIC, for example, so that packet is going to be matched with some flow there. If it does, okay, there are a set of actions that need to be processed. If, for example, it's like just output to the other NIC, okay? So data path is going to do that. It's all in kernel space, really, really fast. But if there's no flow set up here for that particular packet, then it's going to user space. So now the DPIF netlink, it receives that packet and gives it to OF Proto DPIF. So now this OF Proto provider knows about OpenFlow, right? So now it's going through all the OpenFlow rules, all the OpenFlow actions. It's going to build a lot of structures, data structures, and going to push that to the kernel. And, well, I need to execute those set of actions for that particular packet as well. So that's how it works. But it needs to go through all the OpenFlow tables, because all the acceleration is right there in the kernel data path. For DPIF NetDev, that's not how it works. So there's no, the kernel is not involved in the data path. So of course you have device drivers in the kernel space. In those cases, you are either using tap devices or AF packets to read all those packets from the driver. So in that case, so the DPIF NetDev uses the NetDev library and the NetDev providers as well. So it uses those to read every packet. So all packets go through Userspace. If you're using NetDev DPDK, you're using DPDK, so you do not have to go through the kernel space. It's all in Userspace. You have a device driver running Userspace and reading all those packets from hardware, giving them to OVS. So you have a NetDev DPDK, NetDev Linux, which uses TAP and AF packets. So it reads those packets, goes to DPIF NetDev. It has some caching of the flows there. So there's some acceleration here, some what we call exact match cache, so EMC. So if you find the flow there, okay, that's a fast path, going to process that, get to know what the set of actions are, and execute them, output to another port eventually. So it optimizes flow lookups. If there's a miss there, then you gotta go all the way up to OF Proto DPIF, which is going to process all the OpenFlow rules, and set up the cache for exact match caches, okay? So that's great, but you really need a really fast CPU. Okay, so if you're using DPDK, all those things are going to happen on software. So your CPU need to be really, really fast. So imagine that you have a hardware switch that's doing all fast processing, and then you need to go to software, which is running on a control CPU, which is not even sure if they have more than a single core, right? So you're out of luck in that case. So only use DPIF, NetDev, or even DPIF at all, because if you have any misses, if you have a DPIF provider and you have any misses, you're going to have to process on the OFProto GPIF, all in software. And there have been some cases reported that people were trying to port to OVS, and whenever I miss some flow, it's pretty damn slow. They had a very slow CPU, control CPU, so it's not going to fly. Okay, so any questions so far? Okay, so I promised a demo involving VMs, containers, and IPv6. I'm going to do it, but not as I planned. There's going to be some IPv4 involved. So the tunnel user space, it means that we don't have Linux involved, so we don't have VXLAN driver on Linux. Okay, so packets are coming in from DPDK, for example, and now you need to send that through a tunnel. But what's a tunnel? You have to. It's not a new interface device. Okay, so you need to just add a prepend header and send the packets through another interface, and then you need to write that all in software, in Userspace, on OVS. So I'll show you how it works. So here's my setup. I have 2 VMs, 2 network namespaces, 1 in each VM, and that amounts to this complex setup. So it should be very simple, but we have here a port in the container, which is connected to a port on the host, which is in fact a VM, which is connected to a bridge, which has a tunnel port, which goes through another bridge, which goes to an Ethernet port, which is in fact virtual. So that goes to a tap device on the real host, and then through another tunnel there. Okay, and then you have the same setup on the other VM. You may be asking yourselves, why didn't I use .NET CFG? I did.
Wow.
So this is one of the VMs. Okay, didn't get the time to read it, but yeah, shows our network namespace here. It's really nice. Okay, there's some bug here that you need to fix, right? It's the Fedora 23 version. Okay, so so you have here a demonstration of .NET CFG. It's really, really nice, because you can see here that you have the network namespace, which is named foo2, and it got that right. Okay, and it's really, really nice. So we have a loopback device there. We have a virtual Ethernet there that's connected to another one outside of the network namespace, where we have a loopback device. Didn't quite catch these switches, right? So let us see here. Yeah. So when you're using the Userspace data path, I'm using the Userspace data path. So it's not a master. Yeah. Need to work on that. Yeah.
Not supported yet.
Not supported. Okay. So we were supposed to see that this interface here belongs to this bridge, and these other 2 interfaces here, foo2 and VXLAN 0, belongs to beer 0. The reason we didn't see that is that plotnet CFG, right now this current version carries the kernel to see if an interface is a master or a slave of the other interface, which is not the case here because you're not using the kernel to connect to those interfaces. But you'll notice, well, I'm impressed that it got VXLAN 0. You know, because it's not a network device for Linux. Okay, so it's just on OVS. What else we got here? So, okay. So, in fact, here's this setup. We have this bridge here. Okay, and let's see what it's mapped to. Beer 0. You'll see it's a tune device. If you're using the kernel data path, there's a special driver, which is Open vSwitch. So it would not be a tune device, but an Open vSwitch device. The same happens with the other bridge. ENS3 is a virtual net, so the Userspace daemon reads packets from that using AF packet, special socket family. VXLAN 0 is not a network, Linux network device, so it's just a virtual information there in the in vSwitch D. OVS NetDev, well, that's so whenever we're going to create a new data path, OVS tries to create a new data, a single data path for the whole system. So you can have multiple bridges, like we have OutBR and beer 0, but even if you don't have any of those, if you're using the NetDev DPIF, it's going to create OVS NetDev. If you're using the kernel data path, it's going to create OVS system. But there are basically ways to communicate with the data plane on OVS and try to create new bridges. The fact that we have OVS NetDev is an artifact of that. It shouldn't be here, so if anyone has any intentions on contributing to OVS, there you go, we have a chance right here. And for plotnet CFG, there's a good debugging session for that, right? And supporting the Userspace data path is a nice contribution as well. Okay, so let me show you here. So I have this OutBR bridge because if you're going to use a tunnel with Userspace bridge, it needs to go through another tunnel. OVS requires that. It's kind of a limitation, but we talked about that. If anyone wants to talk about that, we can talk about that later. But well, it needs to go through another OVS bridge, which is in Userspace as well. So here we have OutBR, which is connected to the single NIC that we have on this virtual machine. This other bridge has the tunnel, which goes through this remote IP address. Could be multiple hops here, but it's directly connected with the Linux bridge outside of the VM. And there's this foo interface, which with plotnet CFG, we notice that it's connected to some IF2, something like that, which is so here's our container, VF0, which is a single interface there. Has this IP address here, 200.1. And then we have the same setup on the other VM. Okay. So what if I run TCP dump inside the container, and then I ping from inside the other container here? Okay, it's working. But what if TCP dump is run on the bridge itself? Okay, so that bridge is connected to the virtual Ethernet port outside of the container and connected to the tunnel. So it's not going through the bridge because it's not going through the local port of the bridge. So the bridge, it's a virtual Ethernet device which is read by AF packet. vSwitch daemon gets that packet, realizes that it goes through a tunnel. It's not going through another Linux network device. The tunnel is completely inside the daemon itself. It does all the encapsulation by itself. Puts those, so it realized that it needs to go through AltBR, which is the other bridge. But as you'll notice, keeps running here, right? So as you'll notice, it's not going through the bridge either, because the Userspace daemon realized that, okay, it's going through this bridge, but which port of that bridge? Because it doesn't know to go through the local port inside the kernel, which is a tap device. And if it did go there, it needed to go back to Userspace, so it's useless to send it to the tunnel. So I realized that it needs to go through that port, and here you have it. So in fact, what you see here is not a ISMP packet. You see it's a UDP packet, a VXLAN. TCP dump knows how to show the inside of VXLAN packets, and then it shows us that, well, there's a ICMP echo request inside that VXLAN packet. Okay? So notice here that the kernel is only involved in the first port and the last port. You don't have to go through the local ports of the tunnels at all. So it receives that from the virtual Ethernet device and throws it out through the NIC device. So basically, that's the flow here, which the packet traverses. So it goes through the other endpoint of the container, the VM endpoint of the container, goes through Userspace, which sends to the VM NIC. Then it goes through the VNet 0 and VNet 1 on my host itself, okay, which are connected through Linux bridge. So any questions, address to discuss at openvswitch.org, okay? Seriously, any questions?
You were saying no STB. Did you put STB?
Yeah, because the Linux bridge is using STP. I didn't want to show it up. I wanted to make it clear that we had the ICMP packets here. Didn't want them to show up and make it confusing.
Where's the Linux bridge?
It's on the host itself, so yeah. So it's outside of the VMs on the host itself. Have VNet 0, VNet 1, and VRBR 0 NIC connected to the VRBR 0 bridge, which is a Linux bridge, not Open vSwitch here. Okay.
Okay, we are run out of time, so thanks a lot.
Thank you.